In keeping with the spirit of that idea, we're going to record everyone, but we're only going to post people on the website who want to be posted on the website. All right, so we'll start with Greg, and looking for about 20 minutes per speaker.
Awesome, thanks. Looking forward to chatting about something. I'm today going to talk about the reason that I didn't finish my PhD as quickly as I expected to, because the kernel of this idea kind of came into my head when I was like almost done with my dissertation, and then it ended up turning into a whole chapter. I'm going to specifically be talking about doing arithmetic on quantum computers, which is something people were excited about in like 2004 when I was learning how to do like regular arithmetic. But it turns out it's actually kind of getting exciting again. So the reason, let's see if I can get this thing working, or I can just use my computer. The reason I started thinking about this is because I've been thinking about these questions of how we can sort of like verify quantum advantage efficiently on a classical computer. And for this, I was specifically focusing on trying to implement the function x squared mod n. But what I ended up coming up with, it turns out, is relevant for just doing multiplication in general. So it can also be used for other types of cryptography, like maybe lattice-based cryptography, and also things sort of anything that uses arithmetic on quantum computers, including Shor's algorithm. So just to be very clear about what I'm going to talk about today, I just want to implement the following unitaries. So this one I'll call quantum times quantum multiplication, which is two integers, just represented as bit strings in two quantum registers. We're going to multiply them together and put the result in the third register. And the other is what I call classical times quantum multiplication, where you define some unitary that's parametrized by an integer a, and you're multiplying the thing that's in this quantum register by a and putting it in the second register.
And you don't care what it does if the answer register is something other than 0?
That's a good question, actually. So it turns out what I'm going to show you, trivially, you can have something in the answer register, and it'll just add it to that. For simplicity in this talk, I'm just going to leave it as 0, though.
Good.
And the goal is to do this kind of as quickly as possible in terms of gates and number of qubits. OK, so it's going to be a 20-minute talk. We're kind of going to crank through it. I'm going to try to not get bogged down in questions, but you can chat with me later if you're interested in that. We're going to start out talking about fast multiplication in general, not quantum. Then we're going to be talking about a specific technique for quantum multiplication, and then we're going to try to smush them together. The goal is for me to set this up in a way that it's like so obvious, you'll be like, OK, yeah, obviously we should use this algorithm. And then I'm going to actually try to convince you why it's not obvious, and then show you how to make it work. OK, so the classic way of doing multiplication, which is what I was learning 20 years ago when people were excited about this in school, although it wasn't in binary at the time, it was probably in base 10, is where you just basically multiply the individual digits, each of the individual digits, and then sum them up, scaled by the power of the base that you're interested in, and then you get the answer. The running time of this is pretty straightforward. It's n squared, because there's n bits in each of the values, and then you have to take every combination of them. And we can use any base we want. So what I'm going to kind of jump into now is say, what if we instead use the base b equals 2 to the n over 2? So essentially, we're forcing our numbers to each have 2 digits. OK? Then our multiplication looks like this. And we end up with this expression at the bottom, where we have like each of their products and then various factors of b, which is this base, this big base that we're using. Doing this hasn't already given us anything, because if we do each of these smaller multiplications using regular binary schoolbook multiplication, they're each going to take n over 2 squared, and there's 4 of them, so we get just n squared again. We haven't won anything. But now we're going to make an observation. And this is kind of cool. Even if you're not thinking about quantum stuff, you can learn a new thing, or it's probably not a new thing for a lot of you, but you can learn something cool about multiplying numbers. It turns out we actually don't need to do 4 of these multiplications. We only have to do 3. And the observation we're going to make is that when we make this product, it's actually going to be this middle term, and then plus the 2 other terms that we're computing. And the idea is, because we already have to compute x1, y1, and x0, y0 just to find these other 2 things, then we only have to do 1 further multiplication, subtract those 2 things off, and then we get this middle term. And now we've done it only with 3 multiplications, which is pretty cool. Again, if we do schoolbook multiplication for these smaller multiplications, this actually doesn't give us anything in terms of the asymptotic scaling. It's given us a factor of 3/4, but since those smaller ones are still n squared, it's not ideal. But we can do something, I guess, a little more clever and do this recursively. So the idea is we take this big multiplication, break it up into 3 smaller multiplications, and then break each of those into 3 smaller multiplications and keep going. Just kind of looking at it back of the envelope, the depth is going to be log base 2 of this length n. The number of operations will be proportional to 3 to the depth. We can also look at it as this recursion relation, where the time taken to do a multiplication of size n is 3 times the time taken to do a multiplication of size n over 2. But the moral of the story is that if we solve these things, we're going to actually get n to the log 2 of 3, which is n to the 1.58. So we're already winning over n squared super quickly, since I don't have a ton of time. Yeah, so this is actually not exactly Schoenhagen-Strassen, because that one ends up getting down to roughly n log n. This is like a similar idea, though, I guess I would say.
Understand multiplication in terms of some binary matrices.
Roughly, yeah. We can chat about it after if you want that connection, but that's a good question. Okay, so you might ask, why don't we just always do this classically? Because it seems like it's faster, and it's because we have to do this extra additions of these intermediate products. That introduces some constant, which is an extra cost, and that extra constant isn't always worth it. For large enough values, it is. So I looked up the GNU multi-precision arithmetic library, where they make this cutoff when they're multiplying over roughly 2,000-bit numbers. They decide to switch out of the schoolbook method. We can take this a little bit further, actually, with something called Tomb-Cook, where instead of splitting it only into 2 chunks, we split it into k chunks of n over k bits each. And it turns out, I don't have time to talk about it right now, but it turns out that you can do 2k minus 1 multiplications of this size instead of k squared. So you keep winning more the higher you make k. The problem is that you get larger and larger constants out front. But this is the asymptotic scaling that you get for various values of k. As I said a moment ago, you don't want to take it too big, otherwise your constants are going to blow up. And even though the scaling's good, it's just not going to be worth it. Okay, so that's all I wanted to say about like classically multiplying numbers quickly. But we're going to use it in a moment. The main takeaways are that the sort of standard schoolbook multiplication requires n squared operations. There are these faster algorithms, but they sometimes have these large constant factors that cause them to not be worth it unless n is fairly big. Okay, so now I'm going to jump to a technique for quantum multiplication, which requires very few qubits. Oh, sorry. Actually, first I want to talk about whether we can just make these fast circuits quantum. The big challenge here is that, right, we have this like tree structure, and we want to make these circuits reversible. And the problem is that if we need to uncompute intermediate results, as we're doing this recursion, we kind of need to store these intermediate results as we go down the tree and then use them in the uncomputation. So the first try at this was using essentially as much space as the runtime of the algorithm. By being kind of clever about the dependencies between values in here, you can get it a little bit lower. And then actually recently, there was this very clever result from Gidney, which figures out how to do it in what one could call like a tail recursive way to get the number of qubits all the way down to order n, which is very cool. But you know, order n is the asymptotic scaling. If you kind of run the circuits that Gidney implemented in Q#, you see that you end up with something like 12,000 ancilla qubits to do a 2048-bit multiplication. And our question is whether we can make this constant better. And in this talk, I'm actually going to claim that we can get it down to 1 ancilla. So yeah, I'll show you how to do that just now. Or actually, OK, quick other background thing I need to talk about super quickly. We're going to be talking about a fundamentally quantum way of doing arithmetic, which is doing it in Fourier space. So I just wrote down quantum Fourier transform here. And this idea, which I believe originated with a paper by Draper in 2004, is, you know, if the product we want is xy, the Fourier transform version of this product looks like this. And we can observe that then we can implement this product by doing the following. Taking this last register into Fourier space, so that ends up looking like, if it starts with 0, just a uniform superposition over z. Then we're going to apply this phase, which is the phase that we're talking about here. And then we're just going to Fourier transform back, and magically, this product xy is going to pop out. So this is kind of nice. And it's especially nice because you can actually see you don't need any ancillas for this kind of directly, right? So you can do the quantum Fourier transform without ancillas, and then I'll show you can actually apply this phase without ancillas too. So this is nice for saving space. How do we actually apply this phase? Well, I talked about the schoolbook decomposition of xy. It turns out we can just kind of extend it to xyz by putting another factor of a bit of z in there. And we're going to end up with something that looks like this. So we've just broken down this phase into the product of a bunch of smaller phases. The nice thing about this product is that this product here is all of binary values. So this is just saying apply this phase if all of these qubits are 1. So this is just a doubly controlled phase rotation on the bits of x, y, and z. Okay, so we can actually implement this phase by just doing a bunch of doubly controlled phase rotations. The downside is that because we have 3 indices now, this requires n cube gates. So this is a factor of n worse than we got doing doing the n squared algorithm. We actually win that factor of n back if we're only talking about classical quantum multiplication instead of quantum multiplication. And this is because we can just kind of lump this classical value into the phase. We don't have to multiply by the individual bits of it. So then we end up doing a product between 2 n-bit values, but actually one of them didn't even exist before. It's the result of doing this Fourier transform, and then we're shoving this other n-bit value into the phase, and we end up with n squared. So this is kind of nice. We've matched the schoolbook algorithm without needing any extra qubits. OK, so the main question is, can we just smush these 2 things together and get something that's fast and doesn't use very many qubits? We're going to start with this classical quantum case because it's a little bit more straightforward. Our goal is to apply this phase, as I just said, where both x and z are stored in quantum registers. I'm going to generalize this a little by defining this thing I'll call phase product, which is just essentially you give it some phase phi, and then it gives you the product of these 2 things times phi. OK? So we want to split it into the sum of many phases, each of which is easy to implement. The way we did this before was by doing it through a bunch of controlled phase rotations, which we ended up with n squared of them. Let's see if we can use this Karat-Suba decomposition to do this. So this is this fancy decomposition I wrote down before, in which you only need to do 3 multiplications. But now is when we run into a big problem. So breaking down the phase, it'll look like this. And the whole point of doing Karat-Suba is that we were going to reuse the values we computed in the first 2 multiplications in order to make this one more efficient. But they're in the phase, right? Once we apply these phases, it's not like we can somehow magically get x1, z1, and x0, z0 back out, so then we can subtract it off of there. So we can actually get around this, and the way we're going to do it is by rearranging this decomposition. So this is what we had. What we're actually going to do is take these 2 things and just like regroup them over into these terms. So now we have something that looks like this. This would be a bad idea classically, because now the whole point was we were only shifting by like a power of 2. So scaling by these powers of 2 didn't cost anything. But now we're starting to get like complicated things that we're multiplying by this, which seems like a bad idea. The reason it's totally fine here is that these phases we're computing classically when we're compiling the circuit. So we can just do this in classical pre-computation and then not have to worry about it when we're actually running the quantum circuit. So now we actually have a really beautiful structure where in order to implement this phase that we have here, we just need to implement 3 phases, each of which involve a product of only n over 2 bits rather than n bits, with the phase that we have to rotate by adjusted by these prefactors, which we can find classically. So, yeah, we can do this recursively, just like we did in the other case. And we end up with a complexity that has the same recursion relation, and we end up with n to the 1.58 gates again, which is super nice. Let's look at how many qubits we need. So if we just split these registers in half, we can just immediately implement these things, right? Because we just have those values. What do we do about these sums? Well, it might seem like we need a lot more qubits to store these sums in, but remember, we can just do these first, and then because addition is reversible, we can do it in place. So we can store this x0 plus x1, we can just overwrite one of the x values with it. So it almost feels like we can use 0 ancillas. The reason we can't quite get there is because this value x0 plus x1 is just a little bit too big, right? So we need 1 extra qubit to store the overflow bit of that thing. And actually, I don't have time to go into it right now, but this actually could become a big problem because we're recursing. And if we keep doing this every time, we're going to like accumulate these ancillas throughout every level of recursion. But there's a clever trick you can do to basically trim it off and reuse it at lower levels of recursion so that you don't need to accumulate them as you go. Okay, so now we're going to tackle the harder case, which is quantum-quantum multiplication. The problem here is that we have this triple product rather than just a single product of two integers, which I'll call the phase triple product like I defined before. Okay, so the way we did this before was with n cubed doubly controlled phase rotations by breaking down the phase like this. Obviously, n cubed is like really bad. We want to avoid that. Classically, if we needed to compute the product of three integers, there's a really straightforward way of doing it. We just put parentheses around y and z, compute that product, and then multiply by the other value, and it's just still n squared. This is nice. The problem is, for the same reason as before, we can't like get yz out after we've computed it, right? So we need to somehow do this triple product like all at once. But say we break these three integers each into two parts, like we did in the regular Karatsubu method. Then we have to do 8 multiplications of size n over 2, right? Like every possible combination of these two pieces of 3 different integers. One might ask, is there a decomposition like Karatsuba for this triple product? It turns out there is. I don't think anyone's written this down probably because it's like a really bad idea classically, as I said before, right? You should never do this. But in this case, it actually is super duper helpful. And now we're only doing 4 multiplications of length n over 2 instead of 8. We've cut this down by a lot. We get this recursion relation. It's a little bit sad right off the bat because we're like, OK, we got down to n squared. Fine. But it turns out, like we did before, we can break it into k pieces instead of 2. And then we start getting exponents on these n's that are below n squared. And it turns out, due to some subtlety of how you trim off these extra qubits, like I mentioned before, you actually need 2 instead of 1 in this case. OK, so now I want to super quickly chat about depth. Parallelization is actually super kind of natural in here because we're going down these different sides of the tree. So we can, for example, do this one and this one at the same time. We can't do all 3 at the same time without using extra qubits, remember, because we're overwriting one of them with this value. But we actually run into a little bit of a problem if we want to go past depth order n. So yeah, since our runtime is below n squared and we have n qubits, we could hope for getting as good as like n to the 0.58, right? Something sublinear. Surprisingly, we actually run into a bottleneck in that, at least personally, I don't know how to do a quantum Fourier transform using this few ancillas in depth less than order n. So if someone knows how to do that already in the audience, that would make this stronger, which would be cool. But it's an interesting thing to think about anyway. But that's actually the main problem. So if you're willing to use order n ancillas, because you also need to do additions, which, as far as I know, can't be done in less than order n time with just 1 or 2 ancillas, you can actually implement the important maybe operations, these phase product and phase triple product operations, using in sublinear time. So like the hard part seems to have actually gotten easy, like sublinear time in the middle. It's actually this QFT that I seem to be running into as preventing the whole thing from being sublinear time. OK, the last thing I want to chat about super quickly, because I think I'm almost out of time, is how to do modular arithmetic. So far, the phases we've been looking at have the denominator of 2 to the n, because this is the quantum Fourier transform we're doing, right? We're doing a quantum Fourier transform modulo 2 to the n. We can make a nice observation is that if we replace this modulo with whatever our modulus n is instead of 2 to the n, the phase wraps around, so we kind of get the modulo operation automatically, which is really nice. The challenge is that, if you were to do it directly, then you'd have to do a inverse quantum Fourier transform modulo n, which is a lot harder than doing one modulo a power of 2. So what I actually suggest doing is that we can just define some binary fraction. This is kind of like what we do in quantum phase estimation, and just compute some binary fraction that like corresponds to this fraction xy mod n over n, and then that this actually will suffice for our purposes most of the time. And so we've lost our like nice 1 or 2 qubits. Now, this will be imprecise, and it'll require log 1 over epsilon qubits to get to a precision epsilon. And something I'm really interested in is if someone could come up with a clever way to get it back down to order 1. So just to summarize the results, since I think I'm pretty much out of time, for both classical quantum and quantum multiplication, we can get these quadratic multiplication times using only 1 or 2 ancilla qubits. The implications are that we can run Shor's algorithm in only n to the 2.46 times, say if we use this one, using 2n plus log n qubits, which to my knowledge is like the best asymptotic scaling for Shor's algorithm in this much space that people know. Another sort of corollary that I haven't mentioned is that you can actually do an exact quantum Fourier transform in this amount of time instead of n squared using only one ancilla, which is kind of cool. And yeah, to move on to some open questions, as I mentioned earlier, I wonder if we can do the modulo part in also using only order 1 ancillas. I wonder if this QFT can be done in sublinear depth without needing a lot of ancillas so that we can do the whole thing in sublinear depth. Whether we can do any of these things somehow cleverly with 0 ancillas would be very cool. It's not clear to me if that's possible to, like, somehow deal with this overflow problem. And the big question to me is, like, how well can we optimize explicit circuits for this? It actually seems very promising that this could win at practical sizes, with the reason being because we're doing this this sort of like adjusting the phase on a classical computer during circuit compilation. We're actually taking a lot of the work of reconstituting the value in Karatsuba multiplication out of the quantum circuit and putting it into this classical precomputation. So I think we actually are cutting down a lot on the overhead that normally comes with Karatsuba by doing this. And I feel like if we build explicit circuits for this, they could actually be quite fast. That's all I have time for. And actually, unfortunately, I'm traveling tonight, so I have to run pretty much right after this talk. But if you want to chat about this more or have any questions or whatever, here's my email. I live in Berkeley, at least until the end of August. So if you're around, feel free to send me an email and we can chat. Thank you so much for your time.
Where are you going next?
Let me de-mic myself and then.
Yeah, right.
So here. So I'm staying on as a postdoc with my grad student advisor,
Okay.
Norm, for a little while.
Right.
And then, yeah, I'm still figuring out what I'm going to do after that. So,
all right. Look,
yeah,
this was awesome.
yeah, thanks so much. Nice to see you.
Yeah.
See you much.
Hi guys, Shomik here. I'm a Bell student. Today I will be talking about random circuit circuits with non-unital noise. This is joint work with Bill, Kodai, Michael, and Kunal. Noise is something that's present in all types of quantum hardware of today. And I presume one of the challenges of this period is to still get something nice from our noisy quantum computers. Some sort of a nice demonstration of quantum speed up, perhaps. So what is one proposal, like one type of demonstration for quantum speedups? This is random circuit sampling. The task is sampling from the distribution, the final distribution of random circuits. And this is like the bedrock of many of the demonstrations that you see, which try to say that quantum computers are maybe superior to classical computers in some sense. So how does this work? So we have, let's say, a circuit of this form. The white rectangles are random gates, and the pink rectangles are noise channels. And the task, once again, is to sample from the distribution that we get after measuring this final state in the standard basis, let's say. So depending on the type of noise present, this task can be classified into two regimes. What are these two regimes? The first regime is when the strength of the noise is really low. Let's say the strength is some constant divided by the number of qubits. I call this the low noise regime. And the second regime that I will talk about is when the strength of the noise is high, it's a constant for each of the gates that you saw. What happens in the low noise regime? Once again, to recap, this is a regime when the strength of the noise is some constant divided by the number of qubits. There are results which say that if we are in the low noise regime, then all of the noise present in our system can be approximated by a global depolarizing noise channel at the very end. That means that the final state of the system can be written in terms of like a global depolarizing channel. This is the noiseless component, and this is like the noisy component, the maximally mixed state. And the prefactor that you have, the strength of this global depolarizing channel, is something like this. Epsilon here is the strength of each of the local noise channels, and S is the size of the circuit. So in some sense, you squeeze out all the local noise that's present in your circuit and try to like write it at the very end as a global depolarizing channel. Oh, by the way, feel free to stop me with questions. However, the low noise regime is not satisfactory. Like in terms of being a practical model for practical random circuit sampling. Why? Well, first of all, experiments are finite size systems. Whereas these hardness results, or for example, these approximations that we saw of the low noise regime, let's say, these are complexity theoretic statements in the limit of a large number of qubits. So we are talking about scaling up these demonstrations in some sense. And when we are scaling our devices up, the assumption that the noise would go down with the number of qubits, that does not sound too realistic. A more realistic model would be modeling the noise as having a constant noise strength. And so for fault tolerance, having noise to be a constant suffices. We know that these threshold theorems tell us that if we have noise up to a certain constant, then we can just do fault tolerance and get like get the full power of quantum computing. This brings us to the high noise regime. This is when the noise strength is a constant. Like I said, this seems to be much more realistic in terms of a model of like what's really happening in hardware. Now, if the noise that we have in hardware is only depolarizing noise, then we have results like that say that the system tends to the maximally mixed state. And it tends to the maximally mixed state pretty fast in depth. This means that it's classically, like these distributions become classically sampleable up to whatever inverse polynomial precision we want after polylog depth or beyond. So what happens for log depth? There was a landmark result recently which said that the same intuition is true for log depth as well. We can classically sample from a distribution that's close to like 1 over poly precision, no matter what the polynomial is. We can choose the polynomial. And this paper gives a classical sampler which samples from random quantum circuits in this regime with the depolarizing noise of a constant noise rate. Any questions up to here? Okay. Then let me move on to the next slide, where I will talk about types of noise present in real hardware. And the motivation is something of the following form. Depolarizing is just one of the many types of noises present in real hardware. Unital noise is generalized depolarizing. So this family of noise channels are similar in the sense that they are all trying to scramble the system. Entropy goes up when you have these types of noise channels. But like I said, there's also one other type of noise channel present in real hardware, non-unital noises. They are very much they're very dissimilar to depolarizing. And they try to reverse the scrambling phenomenon that these depolarizing type noise channels have. For example, all real hardware has T1 decays and readout noise as well. If there's someone from any of these companies here, I think Ben is from Google, so I presume Google's hardware also has T1 and readout error and these non-unital effects. And sometimes they're even dominant. Entropy decreases when you have, let's say, this family of noise channels.
What T1 decay?
So T1 decay is like a non-unital noise that you have after each gate. So each gate is biased towards a certain pure state. And that's the T1 decay. So one model of these types of noises is like this damping noise. You can think of it as a qubit reset type noise. It resets your qubit to the 0 state with some probability. So this models T1 decay as well. So what happens in the high noise regime now when both of these types of noises are present? Amplitude damping and depolarizing. So depolarizing tries to scramble the distribution like we saw. Now when we have those layers of random gates, they try to scramble the distribution too. Amplitude damping though tries to make the distribution tend towards a fixed state, like a pure state. Unscramble the distribution, that is. So there's a fight between these two phenomena, which seem complementary. So who wins this fight?
I mean, regardless of who wins, it sounds like the LXCB score loses, right?
Yeah. That's true. That's true. What we show is that the damping noises seem to be victorious. That's the highlight of our results. What do we mean by this formally, mathematically? Anti-concentration is one property that we study for these distributions of random circuits. What is that? So that's like a flatness property. In some sense, that's trying to feel how flat the distribution is. If it's catastrophically flat, then we have these classical samplers. So how do we measure this? So there are two standard definitions. One is in terms of collision probabilities. If this is low, this just means that the distribution is kind of flat. And the second is measuring like a typical probability, like looking at a typical probability and trying to say that's sufficiently large. For a flat distribution, most of the typical probabilities for these strings will be pretty large. And in some cases, the first definition of collision probability implies the second one. So that's stronger in some sense. All cases do not have this relation though. And for non-unital noises, this relation breaks. Either way, what do we show? We show that when you have a constant, like a constant strength of both of these noises, then neither of these definitions are satisfied. The distribution is not flat at all. This is true no matter the depth of the circuit. And this is true no matter what strength of depolarizing noise is present in the circuit. barring, let's say, full strength depolarizing. That's like the weird case. So whenever you have this damping or qubit reset type noise, you never have this flatness property. What does this mean? Well, current results to show hardness of random circuit sampling are believed to require some sort of a flatness property for the distribution. So these results break. So we do not know that classically sampling from these distributions up to certain precisions that we knew for the noiseless case, we do not know if for those precisions, like classically sampling from these distributions is hard. Then can we actually classically sample from these distributions by the samplers we know from before? No, because they also need a catastrophically flatness, like they need the distribution to be catastrophically flat as well. And since that is not satisfied, the known classical samplers, they break as well. None of them work. Then what does this mean? Well, one question that I leave to the crowd here is, does it mean that we have some quantum signal in these distributions? Can the presence of non-ignital noise indicate that maybe there's a way to get noisy, scalable quantum, like a noisy, scalable quantum speed-up demonstration? To motivate this question further, in the worst case at least, we know that non-ignital noises can sometimes be a resource in quantum computing. For example, there was a quantum refrigerator paper from some years back which studied something very similar. And that's all. Thank you.
Oh yeah, you want a quick question?
I want to understand, actually, it's a question both to you and to the physicists in the audience. How important are non-unital noises in nature from the point of view of how surprising would it be to have a system in which non-unital noise could be essentially completely ignored?
So my perspective is that right now, at least, we do not know how to suppress the levels of non-ignital noise too well. So there's still constant non-ignital noise after every gate, and let's sit and measure.
I'm not even talking about quantum computers, just physical systems.
Right. So my hunch is that non-ignital noises are probably fundamental, but I would let a physicist speak. I think I don't have a good handle on the physics perspective of this.
Do you mean a non-unisolve quantum channel?
Yeah.
Okay, so for that you need feedback. So in nature it's not particularly natural, I would say, but in these systems. Yes.
No, but just the noise channel.
The fixed point is actually mixed state, so probably you don't have too many systems which have that. I mean, you probably won't have many systems whose fixed point is just maximally mixed state.
I mean, non-unital noise seems kind of like a systematic error, right, or systematic bias. And you'd expect that in many experiments, when you notice those, you would just fix them, right, and thereby reduce the noise to being unital.
But
No?
if it is unital, then like its fixed point should be the maximally mixed state.
Yeah.
It seems a bit
Unnatural.
Yeah, unnatural to me.
Maybe we'll take further questions offline.
Okay, yeah.
If you just People use
the whiteboard.
Oh, sorry. Yeah. So I don't have any fancy slides. I actually don't have any results to present either. It's just kind of an open problem. I thought this was an open problem session. I didn't realize this was like a talk about your results session. It is, maybe? Okay. So just something I've been thinking about, and I thought I'd pose these questions. Also, it should be discussion based, so please, interrupt, ask me questions. It's going to be short. Okay, so I was just thinking about these computational problems that we often encounter, where the input to the problem is a quantum state. So, like in traditional computer science textbooks, you'll have these problems where the input is n-bit string and output is whatever. Maybe it's an n-bit string, maybe it's a 1-bit thing as a decision problem. But just think about problems where this is a terrible marker, where the input is a quantum state. So there we go. So the input is either, it's a pure quantum state, ket psi, or a mixed state rho, and maybe you get many copies of it. And the goal of the problem is often to minimize the number of copies used. You're trying to minimize the sample complexity. I'll give you some examples of these problems. Things like, I guess tomography would be a classic example. Tomography. But then there's variants of tomography like shadow tomography that we all know and love. But yeah, you can think of many different examples. There's like this quantum pack learning. You can trying to learn properties of like these could be some special states, like rho could be the Gibbs state of a Hamiltonian. I know you learn the Hamiltonian from it. And these questions are often phrased like this. You have input, as input, some pure state ket psi, or maybe a mixed state rho. And you want to figure something out about this, learn some property, compute some property. And you want to minimize the sample complexity. So you want to minimize the number of copies of k. And then, of course, you also want your algorithm to be efficient. So you also want time complexity to be small. Okay, so this is a nice abstraction for many problems. But okay, what I'm asking is, where does the state come from? So, if you have your complexity theory hat on, maybe you're thinking like, maybe the state comes from a prover or something, comes from something outside your control. And then this is a perfectly good abstraction of the situation. You just have copies of the state, and then that's all you really have. There's nothing more to be done. But let's put our algorithms hat on. Like you're somebody who's trying to do algorithms, and this state might come from a previous part of your own algorithm, right? So let me give you an example of what might happen. Let's say you want to do shadow tomography, and you want to do so you had a previous quantum algorithm that maybe was doing some kind of very difficult chemistry or material science simulation. With a lot of effort, you prepared the ground state. Maybe it's pure, maybe it's ket psi, and you want to do something like shadow tomography. You want to learn many observables of your ground states. You want to compute maybe like n squared different observables, some 2-point correlators, or a bunch of observables that you're interested in because of whatever application. Now, what I'm saying is that maybe this is not the right abstraction, that you just have copies of the state, because in fact, you have the source code that prepared the state, right? You were the one who prepared the state on your own quantum computer. And then you went ahead and you just, went too abstract, and you just like threw away the fact that you were the one who created the state and just said, well, I have copies of ket psi, and let's just go from here and do shadow tomography on it. So depending on the scenario you're in, you may or may not have access to the source code for the state you're preparing. But if you do, you can do better things, right? So in particular, if I have the source code for psi, so what I mean by the source for ket psi is like some kind of quantum circuit. You have a explicit description of every gate. And so you have some unitary like this. You have full gate decomposition. When you put in some canonical starting state, maybe all 0, you literally get out ket psi. And as before, we're trying to minimize the number of copies of psi because this state was really hard to prepare. That's why we're trying to minimize the sample complexity even originally. Right? The intuition is the state is hard to prepare. You want to use as few copies. And here again, the state is hard to prepare, which translates to this unitary is hard in the sense that it uses a lot of gates. So again, we want to use very few uses of this unitary. But you can do more than just prepare ket psi from this unitary. Right? So some examples of things you could do are, for example, once you have this unitary, like you have an explicit list of all these gates, let me call this u psi. From u psi, you can also do, for example, controlled u psi, which is just take every single gate here and make it a controlled version. Its gate complexity is going to be the same. Again, so you should morally think of this operator as also having the same cost as u psi. Like if this had g gates, this is going to have, I don't know, the equal of g gates or something. So this should also be in this model where we're thinking that creating ket psi costs some amount. This is roughly costs the same amount. Another thing you can do is the inverse operation. And you could also do even more exotic things. Like you could do the unitary that creates the complex conjugate of psi, for example. So you take every single gate in your circuit and you complex conjugate it. Okay, so I guess what I'm saying is that having the full source code of preparing ket psi gives you access to other operations, and these other operations can actually help. You can solve certain tasks faster when you have them than when you just have copies of the state. So let me give you an example of such a thing. Right here. Yeah. So say you just want to do full state tomography on a 1 qubit state. So I have a 1 qubit state. And if I just have copies of psi, so I want to learn a 1 qubit state to error epsilon, let's say, to trace distance. So if I only have copies of psi, it's a 1 qubit state. How many copies of psi do I need to learn to trace distance epsilon? Does anyone know off the top of their head? Shout out some answers. Something will be right. There's not that many options.
1 over epsilon squared or 1 over epsilon?
Yeah, it's 1 over epsilon squared. And okay, yeah, those are the only two possible answers. If you work in this, you know that's one of the two options.
Sorry, this is what?
So there's some unknown state ket psi, and you want to write down a classical, a vector with 2 numbers in it, such that the vector you've written down is trace distance epsilon to the actual state.
But then with those controlled things, it's going to become 1 over epsilon?
Yes. So now I'm going to call that full source code. Like, so if I have the source code, which means I can do, this guy, I can do the inverse and so on. Then, in fact, it becomes better. You can do it with 1 over epsilon. And this is essentially the amplitude amplification speed up. Anyway, not super surprising if you thought about this. Here's a fun question. What if I only give you the ability to apply u psi, but I don't give you inverses or control? You can just apply the unitary forwards. Where are you? Are you here or are you here? How many copies of the unitary do you need to learn this? Does anyone want to guess? It's got to be one of these two, because this is strictly in between, right? So once you have the unitary, of course, you can create copies. So this is, certainly you can do this, and source code includes a special case. One of these two. So, sorry?
1 over epsilon.
So that's not votes for 1 over epsilon. Any votes for 1 over epsilon squared? 1 over epsilon squared. And somebody has any votes in the middle? Anyone wants to epsilon to the 1.5 or something? Okay, yeah, so it turns out that this is actually the correct answer. You can do it with 1 over epsilon. You're using only forward copies of the unitary, which is kind of surprising to me. Anyway, so the point of, so this is just an example, but I'm not pitching any specific open problem, but maybe I'm pitching a research direction, which is to take all of the problems that we have already studied in quantum computing, where we have copies of a state as input, and study them again, but with this model where you actually have the source code available. And for some of them, I think we'll be able to get speed ups. And if these tasks, these are used as subroutines in an actual algorithm, then they do have available the source code. So you'll get actual speed ups, like this motivating example that I had, that maybe you created a state that was the ground state of some difficult chemistry molecule, whatever you wanted to do. Shadow tomography, you want to learn a lot of observables. So now if you have a faster shadow tomography algorithm in the source code model, you'll get a better algorithm for this chemistry problem that I was motivating. Anyway, that's all I wanted to pitch. So any questions? Or does anyone have any other examples of situations where you genuinely have the state, but you don't have the source code? That would be just interesting to know, just to contrast, like why you would be in that situation. And also open discussion. We have a few minutes. I finished what I wanted to say in less than 10 minutes, so please, yeah, go ahead.
I was wondering if you could give some high-level intuition for why having the unitary allows you to achieve the faster or the better rate than having copies.
Oh, here, yeah. Why does it help? So the intuition, right? Yeah, I guess the intuition is that you can apply the unitary over and over again. So you can take small differences and magnify them by applying it over and over again. That's kind of the short intuition I have. But if you think of your unitary as being a small rotation by epsilon, if I just gave you the ability to measure that state, you would kind of need 1 over epsilon squared copies to figure out what that epsilon is. Or let's say I promised you either epsilon or 2 epsilon. But if you could keep applying the unitary, you can keep rotating until you rotate by 90 degrees divided by epsilon, and now you've gone all the way to an orthogonal state from what you started, and you leave each other apart. So that's kind of the intuitive version. The more general result here is just that you can learn any unitary, any d by d unitary, given copies of given the ability to apply a unitary only in the forward direction with ordered d squared over epsilon uses of u psi, and this is tight. You need exactly this number of uses, and you can also do it with this number of uses of only the forward unitary, not the full source code strength. Sorry. Okay.
Do you have any examples where the complex conjugate does something?
No, I don't have an example where it helps a lot. Although yesterday William told me there's an example.
Yeah, in some of these like Bell sampling things, you can get slightly better sample complexities if you have a state and its complex conjugate.
And you can also do crazier things with the source code. I don't think this is an exhaustive list of the things you can do. Like one thing you can do is with source code, you can create the following state. Maybe this follows from having the control operation actually. Anyway, but you can do things maybe that I haven't imagined in these 3 examples I gave down here. Yeah.
So I think if your state is produced through a low depth circuit with measurement, but you are not allowed to extend the depth of the circuit, then in that scenario, I think you cannot have a unitary that repairs the state. But rather, you only have copies.
So you can extend again? So you have, what's the setting?
I mean, you have a low depth unitary that's a low depth circuit that prepares the state,
Okay.
but this circuit involves some, say, mid circuit measurement. And yeah, if you want to have a unitary, like pure unitary that prepares this state, then you will need to do amplification, and that requires extending the circuit depth. But if you're limiting the circuit depth, then at least I don't know a way how this works.
Okay. So you're saying if you have measurements. So I also suppose it depends on how much ancilla and so on you have. Like, can I just purify the whole thing? Like, instead of doing the measurements, I just do it coherently. And just for example, you can ask, what does the source code for psi even mean? And what I mean for that is you prepare purification where you trace out some qubits and then you get psi. So if you had a circuit which prepared some state ket psi, which had a bunch of measurements, one thing you could do is just.
Sorry, I mean like there's some success probability. Like you need to amplify that success probability.
So don't you have to amplify? You're saying maybe there's some circuit with some very tiny probability produces ket psi or rho, and we post-select on that.
Right.
Okay. That's right. Okay. Yeah, because that could be an example where you post-select on an extremely unlikely event. You got a state. Yeah.
Another setting I can imagine is one where you have partial information. So for example, if you run a circuit and then there's miscalibrated gates or noise, then you know what unitaries you try to apply and reasonably well whatever, but you don't know some other ones. So I guess that feels like in between the two settings.
Right. You're saying like noise, right? So like you have an idea of what you were trying to do, but then there's this noise which is outside of your control, and so you don't really have the source code because noise happens. Yeah, that's a good example for sure. Yeah, so I think the model where you do have this, just assume you have copies of rho is certainly well motivated, especially outside of algorithmic context. But I haven't seen too much of a systematic study of like what happens when you do have access to the code. So pitching this out. Yeah, research direction. Any other questions, comments, thoughts?
Just a comment. Isn't there an easier argument of why with u psi you can do 1 over epsilon? So you can just implement control u psi.
So you're saying from u psi you could control u? How's that? I mean, in general, if you know an eigenvector of u psi, you can go from u psi to control u psi.
Well, if you have, you're saying if you have the circuit or if you don't have the circuit?
Have the circuit.
If you have the circuit, then
Oh, you have an explicit description of the circuit.
Oh, sorry, that was a third.
Oh, that's the third thing. Yeah, that's exactly. Yeah, this is. I should maybe draw a box around it. What I mean is, you just have the ability to apply u psi as a box, but you can't look at it and like invert it or make control versions. So this was kind of surprising to me. Like the source code thing is just empty.
so this is without the source.
Yes, this is without the source. So this is where you just have a black box.
So how do you do that?
How does it work?
It's a special case of this result, which is that you can just learn a d by d unitary using d squared over epsilon uses of the unitary as a black box, and then this is a 1 qubit state, so
So
You know,
the
D
O there has a D squared.
it has a d squared. Yes, that's right. And this is a result that we had earlier this year. It's joint work with Jungwon Ha, Ewan Tang, and Ryan O'Donnell. It's called optimal tomography of unitaries, something like this. Tomography, unitary, and optimal. Define this, because we proved both the upper and lower bound this way. It's the word optimum in the title.
I mean, maybe one of the main reasons why you would only have the state and not have these unitaries is that someone only wants you to have the state, right? As in quantum money, as in copy protected quantum software, right? I mean, it's like, okay, you know, we a lot of cryptographic functionality is based on the limitations of quantum measurement, right? And it's like, if I just give you UPSI, then, you know, by using it enough times, you can recover all of psi. Right? So all of that goes away then.
Yeah, that's definitely true. So, yeah, crypto motivated applications, it's very reasonable to just have copies of state.
And also maybe you is implementing on the different architecture. So when you actually implement your architecture, you incur polynomials. Like if you prepare my
But in this scenario, you're imagining somebody else has a quantum computer, creates ket psi on it, and then transfers the quantum state to my quantum computer. So now you have to like have two different quantum computers talk to each other with the quantum internet or something.
Or like psi is the outcome of the physical process.
But then how do you get it onto your?
That's a good point.
I mean, I suppose you could imagine like some kind of yeah. Or maybe it's not really a quantum computer at all, but it's like some kind of actual physical device that just thermalizes and lowers the Gibbs state. So, yeah, certainly there could be situations with that. But just pitching this as a direction for algorithms that people want to do on things like giant states of difficult molecules and so on. People really do want to apply shadow tomography or classical shadows and so on, and all of them have epsilon dependencies that are far worse than quantum epsilon. Like shadow tomography has epsilon to the 4, I think, in the denominator, and classical shadows have epsilon squared. Maybe you can improve them.
So when you have the whole source code, what techniques would you use to show a lower bound, if any? And in particular, like, is there a lower bound of 1 over epsilon for this problem? When you have the whole source code.
Yeah, when you have the whole source code, it's kind of hard to get a handle on how you go lower bounds, because it's you're in the realm of like the setting where we have trouble pulling time complexity lower bounds. Like for example, in this setting, we assume you have black box access to you, so then you can put lower bounds because you use Oracle query complexity lower bounds. Even with source code, like one partial thing you can do is just give yourself access to all of these guys, these black boxes, and then prove lower bounds. Again, with query complexity arguments or communication complexity arguments. I don't know what techniques you can use if you genuinely have the source code. That seems too hard.
For example, like in the one case, if you have the right source code, it's true, the right ability to run. Just read the matrix elements. So it depends how it's given, no?
You're saying like if it's just like one gate, you can just read the name of the gate.
Like the point is, depending on the problem that you're doing, like somehow a very simple circuit already gives the answer.
Right. But you could have like some kind of very obfuscated way of creating a state.
Then it's very source code dependent, right? What's the exact circuit?
You're saying proving lower bounds in the source code model would depend on how the source code is, how bad you do. That's true, yes. It might be just way too hard to prove lower bounds in the source code model. You might have to just go ahead and give yourself black box access to a few things that can be derived from a source code. At least that gives you some evidence that can be proved out.
So do you have examples where do you expect this separation only to be polynomial, or would there be much larger separation?
Yes, that's the question. I don't know in general, like for just this question of with source code, can you get more than a polynomial speed up? But I think one thing that can be shown is if you only have, for example, the ability to create, so if the only thing you have is the ability to reflect about psi. So most of these algorithms, often the thing we use is the ability to reflect about psi. I think if you have only the ability to reflect about psi, any algorithm that uses this reflection operator like k times, I think you can convert an algorithm that uses only copies of psi and uses k squared of them. So at most have a quadratic speed up. If the only property you're using is a reflection property. But I don't know what happens
Is that true? If you get a controlled use, is that the same thing?
I don't know how to deal with the unitary in general. The thing with the reflection work that's nice is it's fully specified. Right? It's just that the reflection is just on side for phase of -1, everybody else it does +1. The unitary could do other things elsewhere, so you have to argue that it's not able to use that other fact, whatever it's doing on the rest of the Hilbert space. On the other hand, it cannot depend on what's doing on the rest of the Hilbert space because the algorithm presumably should work directly with any unitary that prepares get psi. So it's plausible one should be able to extend these lower bounds to the setting as well, but I'm not sure how to do that.
So black box access to U psi is sufficient to construct or approximate U psi inverse by the inverse Sullivan-Kitaev constructions. I'm not. Doesn't this allow one to actually do black box constructions of control U psi? U psi inverse is definitely possible.
That's right. Are you asking if given access to U without any knowledge as a black box, you can construct control U?
Yes.
No, it's a proven.
It's a proven thing. But you can construct, but with black box access, you can construct U inverse.
Not efficiently.
Not efficiently.
But I mean, with exponential time, you can do tomography.
With controlled U, you can construct U inverse, I believe.
No, there's a way. The inverse Sullivan-Kitaev theorems show how you can approximate U inverse.
But that wouldn't be efficient in the Hilbert space dimension.
No.
That's right. Maybe for 1 qubit it's fine. General it wouldn't. Yeah, because like there's these classic old questions like inverting a permutation, which has an exponential lower bound, and that's exactly the question at this point. You have access to the unitary in one direction, but
Okay, and I think that resolves it. Yeah, it's just you can do it, but it's not efficient.
Right. That's probably true.
You get the d squared scale as well.
But D is Hilbert space dimension, or
Yes, the Hilbert space dimension, right? Because there's like d squared real, numbers to describe a unit.
Right. Okay, then I think I come back to saying this is another way of showing that this is required.
I see. So you're saying you think with the inverse space Sullivan-Kitaev stuff, you actually use d squared over epsilon?
I don't know what the numerator is going to be, what the polynomial in the Hilbert space dimension is. I'm not sure.
Maybe. Yeah, I mean, so it's possible to get some poly d over epsilon using other techniques, like for example, we just use it. Actually, I'm not sure. Oh no, maybe it's still possible. You do this thing of you take U psi and you apply it to half of a maximally entangled pair, and then you just do full state tomography on the outer state.
Right.
And this will give you something that here's not d squared though; it'll be worse.
Yeah.
Oh wait, that'll also give you a worse epsilon. Yeah. Okay. I don't know how to compare with Sullivan inverse results, but it's interesting to look into to see if that's a different way of getting this.
Yeah, should we take a break and come back?
Should we thank you?
Oh, no, I think we'll make it. We had a break.
But if you're giving the algorithm task, like looking at the circuit, like that's totally fine. You just stare at the circuit and learn
Yeah, two things. One of them, like one scenario where the method is like only one out of is like what's a class where you know you have the states are proofs and also want to test something about them, right? Like you don't have a succinct encoding of them.
Yeah, for sure. Any kind of proof or verified system, whether it's the crypto setting, that makes sense.
Then another thing is that these guys from, I forget their names, from Canada, but I think they've been working on like exactly this sort of.
They're concepts where you are given a black box history and you want to compose it.
Well, I think they're even trying to get like tomography algorithms. Like you're given a unitary differentiation of mixed space, and then you'd like to do tomography on it. And for like spectrum estimation, I would show it to you about my computer right now.
Maybe I know what you're doing.
And they're using tools to like quantum together values, transform.
So you can do better state tomography if you give me a unitary position state. So general state tomography goes like D over epsilon squared.
Right.
The stuff that you guys, for example. Yeah, I mean, it's like pure states.
Oh, yeah.
Let's say, so it's pure because I want to talk about unitary. So like, there's a pure state, you don't learn that they're epsilon. If you use this algorithm, it's D over epsilon squared, which is tight. But if you have the unitary that makes it, it's actually only D over epsilon. But you need to use its inverse in these cases. Because they use quantum singular value.
Yeah.
They even need to control.
Yeah, I think they've even been claiming to me that like some of their stuff, like this QSBT idea, can give you results in the model where you're just given sent me some draft or something. It wasn't for tomography, but it was for something that was close enough to tomography that I felt like I might be hitting that one.
Possible, although my hunch would be that it's probably not the best way to do it. Using QSBT would only help you the state.
Yeah, I mean, I'm no expert on it, but you know, I've been waiting for like some non-representation theory when I'm getting D squared over epsilon squared.
Right. I mean, like shadow tomography might give this.
Possibly, if anyone ever actually finished looking at it right now. The other question I had, I guess, is do you have any examples where like probably
You don't get an improvement in the dimension dependence. Like so many epsilon.
Sure. Like maybe there's always a generic like epsilon, possibly.
I don't know. It's kind of subtle because sometimes you need both the inverse and the forward direction. Sometimes you only need the forward direction.
Yeah.
It'll be hard to say something very general.
I guess I'm happy giving you both directions.
So, for example, if I give you a CPTP map that created a 1 qubit state row, and I give you the source code, so you can implement the CPTP map. It's not clear to me Actually, what does inverses mean for CPTP?
But are you saying like you give me a map that so it will output a mixed state, but I don't get a purification?
So yes, if I give you a black box and implement the CPTP map, you put in ket 0 and it always outputs rows. And now if I allow you to apply this map as many times as you want, so just like in this middle setting where you can apply the unitary that created psi as many times as you want, or whatever setting. In this setting, there's no for learning and arbitrary 1 qubit.
Or it's not a unitary.
That's right, yeah. CPT. But it's a CPT map. It's not a black box. So it's outputting a mixed.
Yeah.
So like there's no speed up. Like
That's believable.
you'll pay 1 hour at a square.
I guess I'm happy just to think about the case where you have unitaries, like you get permutations. Like it seems plausible to me that if you've ever seen a
Actually, sorry, shadow tomography stuff has horrible epsilon.
Yeah.
It's already epsilon to the 4.
Oh yeah, but maybe you could get an epsilon squared, you know.
Maybe. I actually don't know. I thought about it for a bit.
But do you know like normal tomography do the rep theory algorithms that can use for the rep?
I don't know.
Like I guess like, even for like the pure state
Pure state tomography, because this paper by these guys that you were talking about earlier, I think you can get D over X. Mixed state tomography, I don't know. I guess if you have a purification and D squared thing, like it's double the numbers.
Yeah.
Double numbers. Yeah, you're right. They're out of the
Yeah. But yeah, I mean, maybe they have ways of doing it, but I guess they're not using representation theory. But I wonder if like the representation.
I can certainly find it. I know. So what does it do? It just makes some like epic joint measurement.
Yeah.
Yeah, I don't know. That's not the kind of thing that gets fed up by this. Like usually,
I see.
what you want is like to do amplitude. That's the usual way to go.
Yeah.
You know, most quadratic speed of the
So the determinative thing
I mean, it would be odd if like you always got quadratic speed up and like generically
like you know differently. It's possible. Maybe the algorithm will be entirely sequential. Or
I mean possible.
Like you need a stronger type of any algorithm works in the copy setting, but also has this extra format. Can then be converted, but not just being a algorithm. But maybe such a format algorithms always exist.
So like what you have written up here?
The middle row?
Yeah, it's a black box. How can you usually like without
Oh, I just meant like once you learn the unitary, you can also learn what it does. That's the first column. Get psi will just.
and so like this 1 over epsilon comes from is unitarian D squared over epsilon?
That's right. Yeah. And D is 1.
So if you're trying to like your state is not just 1 qubit. If your state is not just like do you still have scenarios like this, or like pretty specific to that?
So yeah, so in general, it's like the state. I think it's still true that with the source code, like you said, give us U and U inverse. You can learn if it's U over epsilon or use the cubic which is a quadratic epsilon speed up. Tomography.
I mean, even this is a quadratic epsilon.
Right. But I'm saying even in the general D case, if you give me U and U inverse, I can do D over epsilon. But if I just have U, I don't know.
It seems weird to me that like, what are you going to apply U to besides all of your state, right? Because like,
right, because you don't know anything about it.
Yeah,
other
like
than
Oh, it's much cheaper than Scopus, but perfectly fine.
At first I was like, this is confusing, I understand.
Yeah.
Okay, you applied for 0, then you get size. And you applied for
Yeah, I mean, I agree it's a very foolish thing to do.
You could think of a scenario. I
Interesting.
mean, you can think of where epsilon is extremely tiny compared to d, right? Epsilon is like 1 over d to the 10. And this might still be better than a. Like, just go learn the entire unit because you only pay a d squared penalty, but your epsilon was d to the 10, so it's still a d to the 12 algorithm, whereas if you did like state tomography, that would be d to the 20.
But I guess still the question is like, you know, if I only care about applying it to the
Yeah,
zero state.
it feels wrong. Right, right. So there should be a better algorithm, but.
But I forget, how does the algorithm?
Maybe
It's not
you
even
like
given
control apply it to the all 0 state. Like, you can see that being helpful, but still not. Still apply it to any other state. I don't.
My algorithm feels bad now.
No, but like, it seems like that's like it. You're learning the whole unitary.
Yeah.
You just need one column.
The algorithm, the way it works, it really kind of needs you to learn the algorithm. Yeah. Every step of the algorithm, you learn some course, and you bring it back to identity and inverse. And so every stage of the algorithm, you have stronger and stronger guarantees of how close the unitary is to the end. And this lets you learn it better and better. So we start from an algorithm that learns a unitary to constant error. Kind of just boosts error. But it only takes one. But yeah, so that algorithm definitely needs to be inversely symmetry.
No, it's fine.
Not in any obvious way. Like we did think about it for a little bit. Maybe we talked about it for like half an hour. I think it should be possible, but we just don't know. We're probably not using this quantum singularity.
This expression is quite a very mind.
So USPT, like you
Well, I know it's just really generous. So like there's a volume of sets that we know.
I literally know nothing about it, but.
No, I would take it encompasses something that's very good. And just not all things. Like it doesn't encompass your representation.
And then that was when I was back on Arrow. Totally independent. Some things were discussed. What was mine? That's later.
Yeah, I know. And it's the two is that causes things to say never so that's the thing. Yeah, I mean you really don't want to do anything. Because these are part of what resembles is not compliance. Think about it, but to finish
then in the end, we give it to him that PhD project. Goes through a bit, doing a bit scary how much stuff, and then he generalizes it. But it was all interesting about the applications.
You were excellent on this.
It just happened that
Oh yeah, well, I was many times they chose me for your
not even thinking about
Of course. That's all you know. Maybe.
And I think that in the end, it's well, it's on this type of
I know, like I just like sort of like
added section. It was part of it we're interested in, and then we're focusing. But yeah, Noah just really motivated group like
Humans can mount iterative.
it's mainly involved in
this is also highly interesting about this too.
Again, Greg was also using something like
it's very nice. But I have to think that your favorite problem was still carry on. I think quite a lot of the people. I always assume that they're not very good.
George is fine. I see so successful in do you know?
Oh, I know. Yeah. I suppose, yeah. I
Oh,
don't.
he's absolutely. He's so let's say he really thinks that like for now,
unless you have somebody these squares just like
absolutely.
worst case you can just
No. Yeah, I do. You are. Somebody else can talk.
So
we do refocusing in a way that I first said.
That's
We also have ask for an epsilon approximation to the molecules.
right. And to have some.
Yeah.
Which you combine with an epsilon approximation. Never approximate using something that I think that's the way. So our work
Why would it not
in the name.
Compact group, you just have to have some procedure that.
So the work in that case, then it should work for instance.
So like
It doesn't remove it. It doesn't solve my problem with these squares, so the sequence level.
it doesn't solve that problem, no. But I feel like your method should allow universal refocusing without exact.
Yes. Well,
Maybe.
we don't need fundamentals this time.
And you don't need.
There's many aspects which is not in our paper, it's not discovered later, which is also look at the dynamic decoupling literature.
Yes, there we
No, they knew very similar instructions to what we end up using. So, Zola, Neil, Larry, and Decoupers. Because it turns out that the instructions we had discovered kind of ad hoc. Really visualize the network so that it draws out like an ordinary circuit over a graph. No one needs
My first day of the gym, I was like 5'11",
So do you
I don't know why it's got more different. Black box accesses. Also, this is, I guess. Well, if you have a system like that, if I have you and you and us, secret control view.
I looked it up actually. There was this paper. There's a actually the local theory is very strong. So it's
yeah, but when you're climbing half the time
you can't implement control unitary even if you have access to unit universe. So let me look it up actually.
So this might actually not work because.
You mean that you can't do
I think I'm cured of
amplification?
No, you can't get the control. And I think the one over epsilon with source code, right? At least the way I would do it. Maybe there's another way to do it. With source code, but the obvious thing is you use control U.
Sounds like this method was tomograph unit
That's right.
entry by entry. Precision one epsilon.
Yes.
Then we could have the source code.
Right. Yeah, exactly. Yeah. I forgot to know of this.
Yeah.
Lighter research.
Instructions.
Don't care about an exponential n because this is the d squared problem, which is.
Well, they say something pretty strong.
The null next match.
Even with any number close to unit, that's
Wonderful to meet you. Yeah, you too.
with a non-zero probability of success for all. I mean, to be fair, so for some view, obviously, it's possible, but
Beyond excellent.
so there's no general purpose way of doing this.
Whose context like to any group that is really useful. Of course, the spin chain.
Yeah, that's a good question. So, yeah, you did talk about really well. Yeah. I didn't quite understand.
Okay.
I guess let's do
Right, okay, so that's related, but.
So big thing, spin change is always. Cannot make useful but it seems that any system coffee, there's a great.
Yeah, yeah.
That's right, door.
No, I think you do that.
That's exactly
I guess they're saying that if you know the superoperator, there's a phase ambiguity.
It's basically the season of the feature or if you want to see that code.
Yeah, which does matter when you need to control it.
This is something I think is very principle use mathematic codes. So if I give you any system, that's anything. I find this interesting.
I mean, I don't know.
It's just a toss. So I guess one thing that could go wrong is like maybe tomography. It's like yeah, it's true that.
I'll give you some extra, a little extra time.
Yeah. 5 to wrote down this unitary distribution. I just have the constraint
I mean, technically, I guess that's right.
Oh, yeah.
We should. I think we're going to start again, and we'll have
Thanks, Bill, and thanks for all the organizers for this very nice workshop. And today I'm going to talk about this our new classical algorithm that simulate experimental Gaussian Bodon sampling by USTC and Xanadu. And I'm happy to talk about the details, but due to the time limit, I made this slide really high level. So I'm more than happy to talk about the details offline. And also you can find the details from this paper. And before I begin, I just want to thank all the collaborators, Min Zhao and Yuri from Argonne National Lab, and also Bill, and also my advisor, Liang. Okay, so over the last 5 years, we have seen this first quantum advantage claims, first by Google using random circuit sampling, and also USTC and Xanadu using Gaussian Bodon sampling. And they claim that for a classical computer, it's going to be really hard to simulate their experiment. That means in a reasonable time and reasonable computational resources. But we have to keep in mind that these kind of experiments are really noisy. So that means there can be a way to take advantage of this noisy nature to invent a classical algorithm that can simulate those experiments much more efficiently than they expected. So that's going to be the motivation of our work. And we show that we can simulate this Gaussian Bodon sampling type of experiment using our new classical algorithm. So before I talk about our new results, I just want to briefly talk about what Bodon sampling is. So Bodon sampling was proposed by Scott and also Alex Arkhipov. This setting is really simple in principle. You just generate n single photons, and then you just put them in beam splitter circuits. So typically, this beam splitter circuit is just a layer of many beam splitter. And then after these photons going through this beam splitter, they constitute large amount of interference between them. And then we eventually measure the alpha photon number pattern. Then using the hardness of computing the alpha probability of such a circuit, Scott and Alex Arkhipov proved that simulating this circuit is hard for a classical computer under some conjectures. But and then after this proposal, many experimentalists tried to implement such an experiment. But it turns out that it was really challenging because generating this large number of single photons was really hard. The main reason is that the current technique to generate single photon is mostly probabilistic. So that means if you want to generate like 100 photons, then we have to wait a very long time to see this all 100 photons at the same time. So that means this Fock-state Bodon sampling is quite hard. So that made people to change the problem slightly. So instead of talking about Fock-state or single photon input state, people started to talk about Gaussian state, or more specifically squeeze state. I'm not going to talk about the details of this squeeze state, but this is basically a certain type of proposition of photon numbers, which has been studied a lot in quantum optics community, theoretically and also experimentally. And what's good of this squeeze state is that we can generate this state deterministically. So that's why people start to choose this setup to demonstrate quantum advantage in an optical platform. And all the mathematics logic goes similarly. So just using the hardness of computing the alpha probability, we also show that the hardness of simulating such a circuit. Okay, so and then this using Gaussian boson sampling, many experimental groups started to implement this experiment. And what is the real goal of this experiment? The goal is that, first of all, we have this hardness result. So that means for noiseless cases, we don't expect there a classical algorithm that simulate this noiseless boson sampling in a polynomial time. That means asymptotically it's hard to simulate. But this is not the case for these near-term devices. We know that these near-term devices have a lot of loss or noise. So that means we should not focus on this asymptotic scaling, but we have to focus on certain finite size quantum advantage because of this noise. So why is that? So the reason is, if we just, without correcting the error, we just increase the system size, then of course the noise will accumulate in your system, and everything you measure is going to be noise instead of any interesting quantum signal. So that's why we have to focus, instead of talking about asymptotic scaling of using these NISQ devices, we have to focus on this certain size, finite size quantum advantage. So, but still, we have to have a large enough system size that leads to this Goldilocks regime. That means system size has to be big enough for classical computer to hard for classical computer, and at the same time, not too big for noise to dominate the system. So that means we have to find this Goldilocks regime, and to find this regime, we need to understand how well the best classical algorithm can do to take advantage of this noise. And I said this is it can be possibly like inefficient, and that's fine because even these NISQ devices cannot scale up. So classical computer algorithm can be also inefficient in this sense. And so with this goal, people started to implement this Gaussian boson sampling from USTC and Xanadu. And they reported some numbers. So the first number is the output average photon number. They claim that they have detected over than 100 photons on average. And the loss rate was 0.5 to 0.7. That means 50 to 70% of input photon get lost in the circuit. And finally, they claim that it would take at least 100 years for a classical computer to generate even a single sample. So that was the claim of this experiment. And what is this number, this 100 years? This is from the best known classical algorithm we had at that time. So this best known classical algorithm is simply just based on this computing the marginal and use this conditional probability to sample this one by one. So that means the main cost of the best known classical algorithm we had was computing the alpha probability. And we know that this computing the alpha probability increases exponentially. The complexity of computing the alpha probability exponentially increases as the output photon number. And that was the reason why experimentalists really focused on increasing the alpha photon number, even though the loss rate was really high. But the serious caveat of this estimate is that this best known classical algorithm they used did not take advantage of any loss and noise. So this is it can be this number, or at least 100 years. This can be misleading because we are not really we didn't really use the main characteristic of this experiment. So then how can we really use this noisy nature of this experiment? So we first need to understand what noise really affects on the system. And typically, we know that this uncorrected noise often transform a quantum state you have into a classical state. that's easy to simulate, especially as the system size scales. So for example, for random circuit sampling with a depolarizing noise, we know that if we just simply scale up with this depolarizing noise with a sufficiently large depth, then we know that eventually the output state is going to be close to a maximally mixed state. That means we don't have any much interesting signal from the output state. But this is a symptotic statement, and the current experiment is not in a symptotic regime. And the current RCS experiment, random circuit sampling experiments output state, is not believed to be sufficiently close to maximally mixed states. So that was the reason why we believe that they claim that this simulating their experiment is hard. And the same logic just goes in this Gaussian Bodon sampling setup. But with a slight change of this physics. But so for Gaussian Bodon sampling case, the most detrimental noise is photon loss. And this photon loss, if we have this photon loss and just scale up the system size, then it's going to, this paper showed that the output state of this Bodon sampling circuit will converge to a so-called thermal state. So I'm not going to talk about the details of this thermal state, but you can just think of it as some maximally mixed state type in Bodon sampling case, which can be easily simulable using classically. So the same logic here. So for Gaussian Bodon sampling, everything is going to be easy eventually. But similarly to random circuit sampling, the current Gaussian Bodon sampling outcome state is believed to be still far from thermal state. So this thermal state, this trivial approximation is not going to work well. Yeah. Oh yeah, yeah, fine.
In the fourth point, do we know like the rate of conversion?
Yeah, we know some scaling, but I'm not going to talk the details, but I can talk more details offline.
You're assuming here that you say it's believed to be observably far from maximum mixed state, and you said this is because the samples are too small, and also here, right? Is this the reason?
Oh, I mean,
it could be that the noise is not what you're.
Yeah, that's true. Yeah, I mean, this is really just high-level concept that we are not in the regime where they convert noise is so dominant that everything goes to just like some fixed point of the noise. Yeah, I mean, like as Shomi said, the noise type can be different, so uniform it might not be the best for this experiment. But what I'm saying is, we don't. This high-level idea is that this finite system. So it could be the case that the noise has not dominated yet. Yeah. So, but Gaussian Bodon sampling case, the approximation was the fixed point was thermal state, and again, this is finite size system, so we don't think that the output state is really close to the thermal state. So this trivial algorithm, just sampling from this fixed point, is not going to work to simulate this current experiment like RCS and GBS. So our question was basically, can we do better than this fixed point algorithm? And this is the algorithm slide. It has a really high-level idea, so I can talk more details offline. But this is a typical Gaussian Bodon sampling circuit with photon loss. So you just prepare some Gaussian state, and then they go through this beam splitter circuit, and while many photons get lost during the circuit. And then finally, we measure the alpha photon of the output state. And what we found is that we can rewrite this circuit as follows. We have two different parts here. The first part is basically some squeeze state and beam splitter circuit. That means this is still a Gaussian Bodon sampling with a perfect Gaussian Bodon sampling. That means there is no loss in this circuit. And then there is the second part, which is a noisy circuit, noisy channel. So this is basically it has a classical description. So this is basically really a classical. That means the hardness has to come only from the first part, and the second part cannot increase the complexity intuitively speaking.
clear how the long circuits.
Oh, this is really general picture. We can find any.
I understand, but is it efficient to transform the original circuit into the right-hand side picture? Or is it maybe a hard computational task to figure out what's a short circuit?
You mean here, so finding the right hand side.
Yes.
Yeah, that's easy. So we found the system, the program that they can find this circuit. Yeah. So what's interesting here is that there is two contributions for the output photons. One is that the first part is purely quantum part that outputs photons. At the same time, this classical part also outputs photons. So what it implies is that not all the output photons are purely quantum, and many of them can be just classical photons, which can be actually easily simulated. So why this is important? Because then we can just focus on simulating the first part, and the second part, because second part is really easy to simulate.
You say classical photon.
I mean, it has a classical description in probability theory, like phase space method. Like laser is like not quantum in the. Sorry. Yeah, exactly. Yeah, current state. Yeah. Okay, so then, like, how powerful this method is in experiment? We found that after using this experimental parameter, we found that only 3 to 7% of photons actually from the first part, and over the 90% of photons from the second part. So over the 90% of photons are actually classical, and we can just so the task is just simulate this small portion of this Gaussian boson sampling part. So our strategy is to simulate this circuit by using a tensor network algorithm. This is approximate simulation because we have to truncate some part. And the reason why we use this is motivated by the thermal state approximation, in the sense that if we just set this first part to be very trivial state, which is a vacuum state, that means 0 photon state, then that is exactly the strategy of approximating by thermal state. So that's why we say this is a generalization of this trivial thermal state approximation. And we use this algorithm to simulate this Gaussian boson sampling experiment. And the problem is how to verify that our algorithm is better than experiment. So of course, if we can compute the derivation distance, then this is easy, but computing this quantity itself is too hard. This is computationally and also hard, and also we need a lot exponentially many sample from experiment. So this is not a good way. So what experimentalists typically do is to just use many benchmarking methods to rule out all possible Markov distribution people can come up with. So they have used some like XEV type and other type of benchmarkings. But it turns out that like Ben and this Google team was able to spoof all this benchmarking except for this high order correlation function. Here, high order correlation function is basically the marginal property of this output samples. So that means, this is problematic because we don't know which one, we don't know if Google is better or experiment is better in the sense of TBD. But for our case, we show that we can beat this benchmarking as well, including all other benchmarkings. So that is the main result. And I'm not gonna go through all the numerical results, but I'm gonna just show this high order correlation function, and then I'm gonna finish this. So this is this y-axis is basically some score. So the larger the better, and this x-axis is the marginal mode you are going to select to compute this correlation function. And then you can see that all this up to this 6th order, which is the largest order that was calculated in experiment as an evidence of a quantum advantage. We do not observe any clear advantage from experiment over our classical algorithm. So that means all the benchmarking experimentalists provided can be ruled out by our classical algorithm. And also, the important thing is like how much computational cost we have used. And so we have used only 1 hour computation time, but we use like 300 GPUs to compute to sample from this MPS, this tensor network method. So the conclusion is we invented a classical algorithm that uses tensor network, which can simulate the state-of-the-art Gaussian Bodon sampling experiment. And what the implication is that for the future experiment toward quantum computational advantage, they have to focus on decreased loss rates instead of focusing on increasing the alpha photon number. Because that was the main focus of experiment, as I said in the first few slides. But we characterize that that's not the main computational cost, but there is the loss has to be really controlled well. For example, what's interesting is that USTC also implemented experiment in 2023 to increase the alpha photon number. But it turns out that new experiment is easier than the previous experiment 2021 from the same group. So that means they are targeting a wrong figure of merit, and so they have to. The reason was the new experiment has a larger loss rate than the previous experiment. So based on our algorithm, we can finally characterize what is the most important quantity to boost the quantum advantage. So that's the result, and thank you very much for your attention.
One or two questions. Okay, yeah. So you didn't explain at all why you could approximate this with an MPS. So what was the idea of using?
Oh yeah, I mean the basic idea is that after this decomposition, now you have a very small number of photons. So then the amount of entanglement you can have is limited. So that's why we can use MPS.
Is it like a locality? Is it like you make use of the fact that there's a linear spectrum?
The locality is going to be the one, but the main idea is that just think about you have a single photon, then the amount of entanglement you can generate is only very, very small. So that is the main idea of that. So after decomposition, you have a very small photon number. So then,
if they would change the geometry of the Bosel sampling setup,
oh right.
Affect your quality of
right. In this case, so there was some non-local property in the circuit, but that was fine because entanglement was not very large.
So the USTC experiments are all dual.
Yeah, that's
not local.
So that was almost random.
But it's only less than 10 photons, so it doesn't matter in what way you organize it. The entanglement is really bounded.
Okay, yeah, let's keep going.
I have like a big intro.
Just pause this. Great.
Awesome. Okay. I want to talk about not so much a result also, but more of some heuristic idea that we have. If at the end of the talk that idea is broken, you would all make me very happy. And this is work together with Michael Gullens and David Gross, but it also builds on a lot of discussions I've had in the last year with Alex and Robbie and Bill and lots of people. Right, so what's the question? The question we're asking is one that Scott has raised in last year's talk and this year's talk again. Can you hide a secret somehow in the output distribution of a quantum circuit in a way that's efficiently checkable? So can you design a quantum circuit C, which somehow depends on a secret string S, such that, now here comes the setting, as a classical verifier, I can give that quantum circuit to some quantum prover. The quantum prover is going to run the circuit on his quantum computer, sample from the output distribution, and send the samples back to the classical verifier. then the classical verifier will do some sort of decoding, some checking of the samples, which is efficient. And what I'm going to require is that the verifier accepts an honest quantum prover, but rejects any classical prover. So if something here is non-quantum, they will reject. Okay, notice that this is much weaker than requiring that the samples are actually sampled from the correct distribution. Okay, we've seen one very prominent example of this type by Mick Bremner and Dan Shepard back in 2019. They designed some IQP circuits based on quadratic residue codes. And they conjectured that checking some specific property of the output distribution of those circuits would be something that's classically hard. Okay, unfortunately, Greg Meyer, well, unfortunately, I don't know, Greg Meyer, who we've heard this morning in 2019, coded this up and found that this can actually be broken in polynomial time. Okay, so here we are. We don't have any really any candidate for such a scheme at this point. And Robbie has been very active coming up with ideas for such schemes and breaking them again. So what I'm going to present to you today is the first idea, or well, a idea that we have, which we haven't been able to break yet. Which doesn't mean it can't be broken, and I hope you will all be able to break it. Okay, so this is what I'm going to show you, a construction based on IQP circuits plus C0 gates. And the basic idea is we take an easy to simulate circuit, we encode it in a circuit which looks like it's hard to simulate. Okay, so here comes what we have at the moment. Our cheating strategy at the moment runs in time 2 to the log squared n, where n is the number of qubits. It's almost polynomial. We don't know how to make it polynomial. So the question at the end of this talk will be, can we make it just a little bit better? Question so far. Is everyone happy with the setting? Huh?
Price.
Is there a prize? Well, we don't have a pizza prize. I can set a pizza prize. Okay, there's a pizza prize.
Usually these prizes increase the longer the problem remains open.
Yes.
If you just want to reject classical provers, then this is just a proof of concept. Like where do you actually use this?
Where do we use the secret?
Like, why isn't a proof of quantumness protocol valid?
A proof of quantumness protocol is a valid protocol, but we want something that's a little bit simpler. That's not, involving an interaction. And yeah, we want something which is really just, I give you a circuit, you sample from the circuit. Like, we want to make it really basic and simple. Which is why also we can't base it, or we haven't been able to base it on any crypto primitives yet. Okay, ready for the construction? Let me introduce you to IQP degree 3 circuits. Okay, so the gate set is Z gates, control Z gates, and control Z gates. And the circuit, which you can run in IQP degree 3, has a layer of Hadamards, then some diagonal circuit with gates from this gate set, and then a layer of Hadamards again. And then the task is sampling from the distribution. Okay, we're going to keep track of the gate locations in these, well, let me call them tensors, L1, L2, L3, which just have entries at an edge or a hyper edge in the circuit, like 0 or 1. Okay. Now it turns out that the output probabilities, output amplitudes of these IQP circuits are given by gaps of these Boolean functions, which directly correspond to the degree of the IQP circuits. So the Boolean function is just one with linear coefficients L1, quadratic coefficients L2, and triplet coefficients L3. Okay. The important thing to observe is that Z and control Z is a Clifford gate, CZZ is a non-Clifford gate. That's what we'll be using later. Okay, Bremner, Montanaro, Shepard, that approximately sampling from these circuits. If I draw a random IQP circuit of something that's classically intractable up to complexity 30. Good. Okay, now what happens if we add C0 gates? Now we consider the same setup, but before we do the layer of Hadamards, I will add a layer of C0 gates. Any pair of qubits, I'm allowed to add a layer of C0 gates. How does that change the circuit? Turns out the circuit family of IQP circuits is actually invariant under this. How do we see this? Well, if I act with C0 on some bit string, like some state in a computational basis state, I can just equivalently write this as a linear action on the bit string. right? So a circuit composed of C0 gates is just described by this n times n matrix now, right? Not 2 to the n by 2 to the n times n matrix A. The restriction that it's invertible. Okay, good. So such an IQP circuit, IQP plus C0 circuit, is actually equivalent to an IQP circuit without C0 gates, but where I alter the coefficients by A inverse tensor 2, A inverse tensor 3. Right? So I think of these coefficients as tensors, right? They have legs, and so now I'm just applying A inverse on each of them. So far, so simple. Good. So maybe you can already see where this is going. I'm going to take a circuit of this type with a D and C decomposition. I'm going to turn it into a circuit of this type, and the task is going to be to find the decomposition of that. Good. Here's the construction. Okay, so we take linear and quadratic coefficients L1, L2 uniformly at random. Just going to place ones and zeros randomly in a matrix or in this vector. I'm going to draw a random invertible binary matrix A. And then I'm going to take an L3 with order log n many t, log n many 1 entries in it. Okay, so it's a log n sparse L3 tensor. Okay, now the scheme is I take D and A, right? D is described by L1, L2, L3. A is just this matrix, and I'm going to encode it. Well, I'm going to do the transformation that I showed you before, in multiplying by A inverse to come up with this diagonal IQP circuit DA. Okay, then I'm going to send my new tensors LA 1, 2, 3 to the prover. The prover is going to run the IQP circuit sample, and what I'm going to do is I'm going to calculate the XEB score. Okay. Now I can do that efficiently, right? Why? Because I only have log n many non-Clifford gates, so I can use a Clifford plus T simulator to compute the probabilities. So far, so good. Okay. Great. So that's completeness of the protocol. Well, soundness is more complicated. Question is, can you efficiently spoof the XEB given these LAI tensors, which describe the IQP circuit? Okay, one sufficient condition, which I'm going to look at, is can you efficiently recover a matrix, an invertible matrix A prime, and a sparse tensor L3 prime, such that, you know, this multiplied together gives me LA3, and L3 prime is log n sparse, right? Because then I would also have a method to simulate the circuit. Good. So now I'm going to jump one step and just tell you a fact, namely that you can efficiently find an invertible matrix O such that I can reduce this problem to a minimization problem, essentially, over a T times T size matrix, essentially, binary matrix. All right, so you want to find now a binary matrix. Basically, I've done something similar to what William has done, right? I've compressed all the non-Cliffordness somehow into a log n times log n corner of my matrix. And now the task is to optimize over that corner. Okay, so I want to optimize the entries, right? The number of non-zero entries in this new tensor such that I get something which is order logarithmic in n. But naively, the runtime of that, if I search over all the matrices, is 2 to the 3t squared, right? Which is 2 to the log squared n. The question is, can you do better? Yes.
Okay, but for supremacy purposes, this is more polynomial than exponential, like in practice, right?
Yes,
like
it's more polynomial than
get
exponential.
sizes.
Second?
You're not going to get to sizes where this is prohibited.
I don't know. I mean, why not?
Like it's
maybe I can
it's
simulate
slightly
80
above-
T gates or so, but simulating 80 squared T gates is much more difficult. No. That's all I wanted to say.
There was
was a proper learner in Williams results, would that rule out Ghana?
No, because a proper learner in Williams result would still use quantum states, right? So I would be happy with the prover, preparing the state, then learning the circuit, and then sending me the sample. I would be totally fine with it. If they actually prepared the state somewhere in between, I would be happy.
It's Robin's question, right? If you have a circuit that is revealing more information.
If you have a circuit, you have a circuit, right?
The clip. Okay, inside the quantum. No, yeah, that's the point. Like he was asking this question, no?
Right, but in Robin's setup, he was really asking a question about quantum states, right? In his setup, you actually had access to a quantum state. In the setup here, I'm just a classical person who has access to an untrusted quantum computer or so.
Yes. I feel like merging the previous talk, what happens if you got noise with this? If you've got noise, maybe.
Yeah, I think noise is going to make this more complicated. Yeah, I think of this.
It's really not robust.
Second.
IQP sampling is not robust and is even less robust than noise, right?
Less robust than random circuits. I'm not sure about that. I really don't know how robust or less robust it is.
Wait, so if you find this X, do you get a circuit with T gates or with T squared T gates?
If you find an X such that in the end you have the output of this algorithm is going to be X times O, or X inverse times O inverse or so, and then all this multiplied together, right? So then I have a circuit with order log n in gates, if I find an X to satisfy.
So the bottleneck is finding the X, not simulating the circuit.
The bottleneck is fine. Right, the bottleneck, well, depends on how you set it up, right? Another way to spoof this test would be to directly try and spoof the XCP, right? Like bypass actually finding the circuit and do something which scores a high score. I should also say that this actually makes sense. Why does it make sense? Because we know that these circuits that we have anti-concentrate, because already due to the randomness in the quadratic part of the circuit, we have an anti-concentrating. So we actually know what score to expect. Oh. Great. Okay. Okay. So the title of this talk, and I guess also the question I'll be asking is, does quantum cryptography imply classical lower bounds? And I guess before I talk about the quantum version of this question, maybe I should really start by just, telling you the analogy of this for classical cryptography that we know the answer to. And in particular, I claim the following. So we know classically that if, one-way functions, pseudorandom generators, name your favorite, super polynomially secure, falsifiable cryptographic primitive, if such and such exists, then, for example, P is different from NP. So there exists some separation of complexity classes that we get as a result of cryptography. And the question I want to ask today is whether something similar happens in the quantum setting. So, can we show that assuming some quantum cryptographic primitive exists that again is secure against super polynomial adversaries, that there is a barrier to establishing that unconditionally in the form of some, long-standing classical lower bound that we just don't know how to prove, and that you would win $1 million for via like the Millennium Prize or whatever. So if you think about this question for just a little bit, you might expect that for like similarly trivial reasons, there should just be like a yes answer to this question. But it's actually not so obvious. And intuitively, the reason for this is that an adversary, a quantum adversary against some cryptographic primitive, does not operate on a classical input. It operates on a quantum input. And for that reason, it's actually very difficult to relate the complexity of breaking that primitive back to a question about classical complexity classes, which only involve purely classical inputs. And I think kind of the first work that really kind of pointed this out was, or maybe I guess a couple of works by myself in 21, and also joint work in 23, where we showed that there exist oracles relative to which, first of all, either BQP equals QMA in the first result, or P equals NP in the second result, but quantum crypto exists. And so this is actually saying that there's kind of not an obvious resolution to this question in the form of like, if you have some quantum analog of one-way functions, then you must have like, BQP is different from QMA or something. So saying that there exists an oracle, this is saying that any technique for showing that such a primitive implies a separation of these complexity classes would have to go through non-relativizing techniques. And that's in direct contrast to the classical case where these sorts of results hold relative to any oracle. So, at least this suggests that, something different is going on in the quantum setting. And I know at least several people who have interpreted these kind of results as saying that maybe proving quantum lower bounds is actually easier than proving classical lower bounds. Perhaps we could actually hope to have, something like pseudo-random quantum states, for example, where we can just, maybe it'll turn out that we can just show unconditionally that they exist. And we don't run into a barrier like this, like in classical complexity theory. And I guess in this talk, I'm going to tell you why maybe you shouldn't be so hopeful about that. So where do I go next? So, people have kind of struggled to relate these, quantum cryptography questions back to classical complexity questions. But one thing we have been able to do is to, instead of defining complexity classes where the inputs are classical, you can sort of define complexity classes where the inputs are quantum. And in that case, then you can say something sort of like this. So in particular, there's a theorem which I guess we heard about in Tony's talk last week, if any of you went to that. But in case you didn't, this is by a long list of authors. Y 23, where basically they showed that if quantum cryptography exists in the sense that I defined earlier, meaning a crypto system that is not information theoretically secure, it's only computationally secure against polynomially bounded adversaries. If such cryptography exists, then you can define these quantum classes like unitary BQP which is like a unitary version of BQP. And this is different from a unitary version of p-space. It's the set of unitary transformations that you can implement in polynomial time on a quantum computer. And similarly, unitary p-space is the set of unitary transformations that you can implement in polynomial space on a quantum computer. And so kind of the question this leaves is, can we relate a separation of quantum complexity classes like this back to a separation of classical complexity classes? Or is there like a barrier to, showing some sort of a connection? And, I guess this is where, things might get a little bit hand wavy, but I kind of figure that's the whole point of these informal talks. So, informally in some of the discussions I've had and in some of the papers I've seen, what people have kind of attributed to the difficulty in relating a question like unitary BQP versus unitary p-space back to, say, BQP versus p-space, a lot of people have attributed to our lack of understanding to this one question, which is actually a question in query complexity. And it asks the following. I guess I'll call it a definition. So this is the so-called unitary synthesis problem. And it asks the following. Does there exist a polynomial time algorithm, a polynomial time quantum algorithm that gets oracle access to some classical function f such that for all n-qubit unitary transformations u, there exists an f on a polynomial number of bits for which q implements u at least approximately. So again, the statement of this is that it asks, does there exist an efficient quantum algorithm such that for any n-qubit unitary, you can pick some choice of this oracle f, such that with oracle access to this function f, you can approximately implement that unitary. And I guess another way of saying this is basically, can you always reduce the hardness of implementing some unitary transformation to the hardness of implementing some classical Boolean function? And this has been open for, I think, at least 20 years in some form. And intuitively, people have kind of suggested that maybe this is kind of the barrier. Like maybe this is why it's hard to relate questions like unitary BQP versus unitary p-space back to classical complexity questions. But nevertheless, as far as I know, no one has actually, before this talk, proved any sort of rigorous connection between these problems. And the thing I wanted to mention today was kind of a cute observation that I had that you actually can show some sort of connection between these problems. And in particular, maybe I'll write over here. Yeah. So this is a theorem that I observed. So suppose that it turns out that the unitary synthesis problem is easy. So there's a positive solution to this question. There is some polynomial time algorithm that lets you implement any unitary. And suppose that unitary BQP is different from unitary p-space. And so, for example, suppose that there exists some quantum crypto system, which would imply the separation of quantum complexity classes. Then I can show that this implies some classical complexity separation that we don't know how to prove today. In particular, I can show that this implies that BPP is different from NX. So BPP is bounded error probabilistic polynomial time. So this is problems that you can solve by tossing coins on a classical computer in polynomial time. And NX is non-deterministic exponential time. So it's like an exponentially more powerful analog of NP. And a lot of people who I talk to who haven't seen that much classical complexity theory before are very surprised that we don't know how to prove that these are different unconditionally. But this is indeed one of the basically research frontier questions in classical lower bounds. And yeah, if we could prove this, this would be a major breakthrough. How much time do I have? So maybe I can sketch some of the ideas, at least briefly. So let U be something that's in unitary P space. So maybe it'll actually be easier to think about it as proving the converse. So suppose unitary synthesis problem is easy and BPP is equal to NX. I'll show you how to implement something in unitary P space efficiently. Then since unitary synthesis is easy, there exists an F on a polynomial number of bits such that some quantum algorithm implements and kind of the whole idea is to show how if BPP is equal to NX, you can compute this function F efficiently. You can actually find it in polynomial time. And I think this is where I'm probably just going to very quickly skip through the details, but I basically claim that there's a verifier. So you can think of this as an NP verifier that, given a function F, it, in exponential time, can decide if this quantum algorithm approximately implements our desired unitary U that is in unitary P space. And intuitively, the reason for this is that you can just compute all of the amplitudes or all of the entries of this unitary in exponential time in the number of qubits in the system. And you can also do the same thing on this side. So this is non-trivial, showing that if you have a unitary that is in, I guess, unitary P space, that you can compute its entries in classical exponential time, but that turns out to be true. And kind of the idea is we're going to use the fact that BPP equals NX to find this F. And in fact, there's really only one more ingredient that we need, which, I think I'll just state, but maybe not really go into detail about how it's used. It's the Impagliazzo-Kabinetz-Wigderson easy witness lemma, if any of you have heard of that before, which says that if BPP equals NX, then there exists a compressible such F. So in other words, if NX collapses all the way to BQP or to BPP, then it turns out that there exists a function of this form that actually is very succinct. In fact, F can be described itself by some polynomial-sized classical circuit. And then using the fact that BPP equals NX, you can kind of just find that classical circuit efficiently on a quantum device or even by a classical randomized algorithm. And then you can just plug that function F into this simulator Q and get that that U is in unitary BQP. So that's the proof idea. I think maybe the one thing I will leave you with, which is kind of the main question I have that relates to this, is kind of supposing to the contrary, suppose that actually the unitary synthesis problem is hard. And not only that it's hard, but that it's hard for some explicit unitary that's in unitary. So in other words, there exists some unitary transformation that you can implement in polynomial space on a quantum computer, but that such that this unitary transformation not only does not have small size quantum circuits, it does not have small size quantum oracle circuits. And I guess the question is just vaguely, does this imply lower bounds, like classical lower bounds? Because at least intuitively to me, this seems like an extremely strong lower bound, because you're saying like, there's some unitary that you can compute in like a space-efficient manner relative to its size as an n by n unitary, but like it does not admit any efficient implementation by this extremely broad class of algorithms, because it's not just polynomial size circuits, it's like polynomial size circuits with arbitrary classical oracles. And to me that seems like a really powerful class, and I sort of intuitively expect that this should imply some breakthrough in classical complexity theory as well. But I would be very interested to know the answer. And I think with that, I'll stop and take any questions.
So if you were able to show this, would you morally believe you had covered, morally covered everything?
Yeah. So actually, I think it really would sort of cover everything, because actually here we don't even need. We just need that like unitary synthesis is easy for all unitaries in unitary p-space. Yeah. Just like either, so if unitary synthesis is easy in unitary p-space, you get a lower bound, and I'm sort of conjecturing that if it's hard, you should get some other bound. I don't know.
So a negative resolution to your question would not say proving quantum lower bound.
Sorry, what do you mean?
If the answer to your question is false, then maybe we can still prove unconditional.
Maybe, yeah, but I don't know. I think it looks hard.
Okay, but proving lower bounds are hard, but also you can construct harder things, harder unitary and hard unitary.
Perhaps, yeah. I mean, that's sort of exactly the question. It's like, can you do that? Any other questions?
So you're saying this is like the converse to like. So you said if USP is easy for all unitaries in unitary p space, then BQP is not equal to next. And now you're saying, suppose the other thing is true.
Yeah.
What do we get?
Yeah.
So presumably it has to be something that doesn't imply BQP is not equal to next. Otherwise, you're gonna separate BQP from next.
Assuming quantum cryptography exists. But like, if you just show that quantum cryptography implies BPP equals BPP is different from NX, I don't know if that would be that surprising. But I mean, that's sort of the question. It's like, can we get some implication of that form?
So I was just confused because it's.
There's.
I see. Like, I suppose USP is hard and quantum cryptography exists.
Yeah. Then lower bounds follow.
Okay. I see. Yeah.
Okay. Maybe I'll stop there.
So, hello everyone. Thank you for indulging until the end. And we are going to present today some constant depth quantum circuit for UCG gates, uniformly controlled gate, oracles for Boolean function, and application to quantum memory circuits. So the key, I guess, of our construction is that we propose circuits that are in constant depth. And for this, we use some multi-qubit unbounded entangling gates. But first, since we apply our construction to quantum memory, we have a question for you. And the question is, what is a quantum computer with access to memory? So we try to come up with a formal definition. We are not aware of other formal definition of quantum computer with access to quantum memory. So if you know some, please point that at us. And yeah, our model is the following. So we have a quantum processing unit, so a quantum computer with a workspace whose size is polylog in the size of the memory. And then you have an address register. Size is logarithmic in the size of the memory, so you need only log n bits to address and memory cells. A target register of size L. We can pick L equal to 1 for simplicity in these slides. And then you have a quantum memory device that shares the address register and the target register. And on top of that, it has some ancillas and the memory qubits that you want to address. Okay? And the address register and the target register are shared between the quantum processing units and the quantum memory device. So calling a quantum memory device is implementing this mapping here. So you have a function that takes as input the index register and gives you a 2-qubit unitary from a constant size set. And it applies the unitary to the ith memory cell in the memory and the target register. So practically, this means that if you have a normal quantum memory, like the bucket brigade, for example, what you're applying here is a C0. So controlled on the ith memory register, you apply a NOT on your target register. Okay. Any comment on this computational model? Good. Basically, yeah. It's like a generalization of QRAM. Yes. For example, another kind of quantum memory device is a QRAG gate, where instead of applying C0s, as in the QRAM case, you apply control swaps. So like you are swapping the target register here, BT, with the ith position in the memory. And that's something that is used for quantum random walks and element distinctness, for example. Sorry, the question is if this model still capture the bucket brigade. Good question. If our model capture the Q-treats.
Well, you can implement the brigade with qubits. This was done proposed later.
Yeah, like Conran.
Yeah.
Yeah, probably there's a log overhead, probably. I'm not sure. Okay, so for our constructions, we use 3 magic gates. So the first is the Thenin gate. And the Thenin gate is basically applying this function f of x to our target register B. And famous examples of F-in gates are the end function, majority, exact gates, the OR gates, and so on. And the fan-out gates is basically the generalization of C0, where instead of having one NOT, you have other NOTs. Okay, so and then you have global tunable gates, which is kind of basically the product of control Z gates, where you have one parameter for the phase of Z gate. Okay, and yeah, all these gates in the bounded setting are physically implementable. So obviously, we don't claim that these gates are implementable in the unbounded case in practice, but the bounded case is definitely feasible. And also we need these results from previous literature. Well, it's very simple to see that the fan-out gate is equivalent to parity. You just need to sandwich the fan-out gate with Hadamard's, and you have a parity gate. And then the AND and the OR gate equivalently can be exactly implemented in constant depth using linear number of fan-out gates and n log n ancillas. This series of work started with Royer and Spalek. And then to have a more physical implementation of the AND and OR gate, you can use 4 GT gates and a linear number of ancillas. Okay, so while we let you think about this meaning of this circuit, we switch microphone.
Okay, so now we're going to start showing our results. So among many results that we have, we propose a quantum circuit in constant depth for QRAM, as Alessandro told. So that's a depict of the circuit. So try to explain briefly what we need first do some copies of your address register. And when you do the copying, we're going to do some, this part here is we're going to calculate the one-hot encoding of the address, which is an exponentially larger bit string whose nth entry is 1 and the other entries are 0. So once you do this and you need to compute this with using AND gates, and once you have the hot encoding in this register, you just compute like a parity gate. So I think, of course, implementing this AND gates and the fan-outs won't be true, but the circuit itself is quite simple. And then we go. So we propose many constructions for QRAM and QRAG. So we show the best ones we obtain. So for example, we can retain basic linear number of ancillas and fan-outs for QRAM, and just a few number of gates for number of GT gates. If you allow more ancilla, you can decrease the number of GT gates from 6 to 2, and similar to QRAG. And then the last slide, we generalize this to constructing any fan-in gate. And I'm not going to go through the results, but we propose many constructions that rely on different properties of the function you implement. So one of these properties that we came up with is this idea of JR junta that we propose, and we haven't seen this anywhere else. So what we say about a Boolean function is, or any other function that depends. So any Boolean function that depends is a JR junta if you can find a set J if you fix the coordinates outside the set J to any value, and it's important, it can be any value, the resulting restrictions are junta. So a good example is the QRAM itself, because if you fix the address qubit, address entry, then it becomes like a dictator function. So one question for you, to be honest, if you've seen these properties or similar properties being studied anywhere else, we haven't seen anything, and I think it's a very natural one. And I think another question we have is if you have seen any not necessarily constant depth circuit constructions for Boolean oracles. I think that's it on our part, and yeah, thank you.
I guess another thing that we can say is that if you try to implement our circuits in practice and you don't have the unbounded gates in your lab, you can go from a constant depth circuit to a circuit of log k and depth. So the bucket brigade circuit is log 2 of n. With our construction, if you have gates of RETK, you go to log k of n.
I guess another result we showed, I guess in the previous slide, that we generalized, we have even the more general results for these uniformly controlled gates, where U of X is a single qubit gate. And the final circuit is one of the constructions. They started becoming much more ugly. Okay, if no questions, thank you. Okay.
first of all, I didn't understand the result about the puntas. What's the result?
So so one of the constructions like leverages on this property of like JR junta. So we say like the function is a JR junta. If you fix the if there's a set on which if you fix the values, the coordinates in the set to any value, the restricted function is an R junta. So it's not.
This is the definition, no?
Hmm?
Sorry, this is the definition?
There's the definition, yeah.
What's the result?
It's the first line. I mean, if you know your function is a JR junta, then you can implement with that many ancilla and fan out and GT gate. So for example, you can construct basically like exponential number of t plus r. For example, if you can already apply this to QRAM, because QRAM is a subcase of fan with the selection function. And the selection function is a fine example of JR junta. When the size of the complement, the t is log n, and r is 1.
Anything else? No, let's thank all the speakers again.
Thank you.
And let's thank all the organizers of the conference, right?